Hey everyone, and welcome to this explainer. Today, we're diving into the absolute fundamental building blocks of computer logic. We're going to be demystifying programming logic, really breaking down exactly how simple, individual instructions combine to architect those incredibly complex decisions that our devices are making every single day. It's actually pretty wild when you think about it.
So here's our mental roadmap for today. First, we'll hit the core building blocks, then we'll master the sequence, do a little testing of sequence logic, move on to making choices with selection, and finally putting it to the test.
All right, let's jump right into section 1, core building blocks, the foundations of logic.
So, you've probably heard the term control structure before. Basically, this refers to the underlying architecture of literally every single computer program you interact with. Think of it as the framework we use to tell a computer exactly what to do and exactly when to do it. Now, any algorithm out there, and I mean literally any set of instructions used to solve a problem, can be described using just three main control structures. You've got sequence, selection, and repetition. But to keep things super focused and efficient for us today, we're going to zero in on mastering just the first two, sequence and selection.
Moving on to section 2, master the sequence, step-by-step execution.
Okay, so the sequence control structure. This flows straight down exactly like reading a recipe. There are absolutely no detours here. Let's say you want to calculate a person's age. The program reads the birth year, moves straight down to calculate the age by subtracting that year from the current year, and then it simply prints the result. Step 1, step 2, step 3. Boom. It is just beautifully predictable.
It's the exact same thing if the problem is finding the area of a rectangle. You can really see that linear flow here. We read the width and height, multiply them to calculate the area, and print the result. The computer reliably operates step by step in the exact order that we've written it. No surprises. Which brings us to section 3, testing sequence logic. Let's trace the logic flow. All right, I want you to trace this block of pseudocode line by line in your head with me. First up, we let length equal 2 and width equal 4. Next line down, area equals length multiplied by width. And finally, print area. So I'll give you a quick second. Based on the exact values we just read, what is the final output going to be when this sequence finishes running? Well, if you said 8, you hit the nail right on the head. You took that length of 2, multiplied it by the width of 4, and got 8. This completely validates how sequence logic works. It executes strictly, relentlessly, in the exact order it's written down. Now for section 4, making choices with selection. The selection structure. So while a sequence just executes all steps in order blindly, a selection is a bit of a game changer. It defines two different actions depending on the outcome of a specific condition. It basically evaluates an expression to either true or false before it decides which path to take. And honestly, this right here is exactly how computers make decisions. But to actually make that decision, the computer needs a test, right? We use relational operators to create those tests. I'm talking about things like equals, does not equal, or less than. So for example, if we ask if 10 is less than 5, well, that obviously evaluates to false. It's these simple mathematical tests that generate that absolutely vital true or false value whenever we hit a crossroads. Take a look at the diamond shape in this flowchart. You're going to see that a lot because it's the universal symbol for a decision point. By using the keywords if and else, a computer splits its path. So if a condition is true, the program takes the then path. But if it's false, it routes into the else path. It's literally one question leading to two possible futures. Let's look at a practical application. Say we're checking if a number is even or odd. The diamond asks a very simple condition. Does the number modulo 2 equal 0? If that's true, it branches down and prints even. If it's false, it branches the other way to print odd. And just like that, the computer has successfully navigated a choice. Which leads us to our final section, section 5, putting it to the test. Sequence and selection combined. Let's put everything we've learned together for one final challenge. Okay, so our sequence starts by setting x to 10 and y to 40. Then, boom, we hit our selection diamond. If x is greater than y. I want you to evaluate that in your mind right now. Which branch of the if-else statement is the computer going to choose here? Take a really close look at the math inside both the if path and the else path. Based on the decision made back at that crossroads, what are the final values of x and y that are actually going to get printed out at the very end? Let's break the whole shebang down together. Our initial state,
x equals 10, y equals 40. Now, our condition checks. Is 10 greater than 40? Well, no, that's false. So the logic completely bypasses that first block and routes directly into the else statement. It takes the current value of y, which is 40, adds 50 to it, making our brand new y 90. Meanwhile, x remains completely untouched at 10. So our final print is 10, 90.
As we wrap up this explainer, I want you to think about your own morning routine today. If it was raining, did you grab an umbrella? Else, did you grab your sunglasses? We've just seen exactly how simple sequences and true-false selections build the entire foundation of computer intelligence. But really, how much of your own daily decision-making is just a complex algorithm of hidden sequences and selections? Definitely something to chew on as you navigate the incredibly programmed world around you. Thanks for hanging out with me, and I'll catch you on the next one.